Morning, we're Stealth Engineering. My name is Andrew Mew. I'm the Transportation and Construction Specialist on this project.
I'm Amanda Palmer. I'm one of the hydrologists.
I'm Tyler Sonoma, the other hydrologist.
I'm Adam J, the pavement specialist.
And the name of our project was the multi-drain project. Our location was a parcel of land just northeast of the intersection of Hazlitt and Marsh Road and Hazlitt, Michigan.
Okay, our problem was given to us by Ingham County. The residents of Norwood Village needed a drainage design to alleviate frequency of flooding, and we want to improve the road conditions pertaining to pavement and transportation, especially to do with drainage. So the problem was brought to us because some of the residents were complaining about flooding in their backyards, and they were requesting a new drainage system. So some of the things we looked at when we were doing our initial analysis, we noticed that the current drainage system was ineffective and couldn't handle peak flows with the amount of water necessary. And the pavement was in poor conditions as a result of this flooding. So our first objective was to meet all regulations pertaining to Ingham County Drain Commissioner, the Ingham County Road Department, AASHTO, and MDOT. We wanted to design a new drainage network that would effectively eliminate flooding while also minimizing the impact on the residents in the neighborhood. We want to improve pavement conditions that were negatively damaged by the flooding, maintain traffic during construction, as well as being cost-effective and sustainable. So the first step of the hydrology design process was to obtain the initial site characteristics, which include things like soil and topography and rainfall data. We next came up with a conceptual design for our drainage network. We designed the pipes based off the county regulations, and we flooded the water through detention ponds. So this is a map of the distribution of soils in our area. The area is categorized as a dry wetland, so all the soil is pretty marshy. It's in class C and D. The soils are the soils, because it's so marshy, it's filled with water, so it has very poor infiltration and high potential for runoff. And these are some of the bigger contributors to why it was flooding and ponding so much in the area. The next step was to determine the amount of runoff. And runoff is described as the flow of water along the surface of land. The runoff coefficients describe the susceptibility of runoff to occur over a given area as a percentage. And one of the main contributors to runoff is development and developed land. So basically these coefficients come from the percentage of land that is developed in each area. So the 0.75 refers to 75% of the area is developed with things like roads, sidewalks, which promote runoff. These coefficients were used to determine peak flows in our pipe design. So these are the maps that we used to determine rain intensity. The pipes and swales were designed for a 10-year design storm, which had 3.54 inches of rain. The detention ponds were designed based off these maps. The 2-year 24-hour rain map represents the amount of rain that would occur in the event that is 50% likely per year. So we have a 50% chance every year that we will get 2.55 inches of rain. And this map similarly shows the same data, except it's for every year a 1% chance of occurring. So we have a 1% chance every year that we will have 5.5 inches of rain. So our detention ponds were designed to handle these intense storms, and they were also designed to hold the first flush volume, which is the first half inch of rain that occurs during a storm event.
To begin the pipe design process, we had to calculate peak runoff rates from the contributing land. That was done by first finding out what the contributing land was, which was through a process of watershed delineation. We then had to design the pipes to handle these peak flows by using the rational method in the Manning's equation. And then for each manhole location, we designed for the most critical event, which dealt with the time of concentration, or the time it takes for the water from the most remote point to reach each manhole. And for the detention design process, we first started with storm hyetographs. These are statistical analysis done by the Soil Conservation Service that studies geographic locations, and in Michigan we are type 2, and this just describes how water will fall during a 24-hour storm. These incremental values for each hour were then multiplied by the area and runoff coefficient for the contributing watershed to each detention pond, and this gave a runoff hydrograph, and these were used as the inflow values for our detention pond routing. For detention pond routing, we used the modified pulse method, which is the equation shown at the bottom. It's a simple mass balance with assuming a detention pond size and outlet controls. For the conceptual design, we had to find runoff directions and paths. We had to delineate the watershed by using these runoff paths to find low and minimum elevation points. We used roads as boundaries for these runoff paths as they were designed to not allow water to flow over top. We used high elevations and connected them to also create the boundaries for the watershed so that we could determine where water and runoff will be directed. And then lastly, we had to find the lowest elevation areas where most water would pool, to find areas where it was frequent flooding and where we had to focus most of our attention. For the first part of the design, we considered the southern half of the neighborhood. These are the delineations of the watershed. The gray boundaries are the sub-catchment area boundaries, and the blue arrows are the runoff directions. And the red is the main area of concern. Most residents were complaining about flooding. The new stormwater design system. So this was the main location which we focused on. This elevation of 850 feet, it was first considered to put a standard piping system throughout the whole neighborhood, conjoined together and brought it all to one off-site detention pond. However, with this elevation at 850 and regulations of 3 feet underneath the ground for the pipe, this would give very little elevation change to allow a detention pond to be placed off-site with this water running through it. So our design was to split this area we just previously shown into two separate areas and handle them with detention ponds. This area shown in red is 10 acres roughly, and pond 1 is a no outlet retention pond, which would take care of exactly 1 acre of land. So with pond 2, we use swales and pipes with manholes at each start and end of the red arrows, which represent pipes, and the green arrows represent swales. So this 10 acres of land was routed through pond 2, which is a detention pond. This detention pond is 0.4 acres in size, and with the 10 acres of land running into this detention pond, with the regulations, it would allow 1.51 cubic feet per second because of the regulation that states that area times 0.15 is the pre-development discharge. So it meets regulations for the outflow rates during a 100-year storm. It also meets regulations when running the pulse method for the bankful flood values, as it takes 37 hours for the outflow to stop. So this also meets regulations. For the main area of concern, this 5-acre piece of land where most flooding has occurred, we had designed swales to go in through backyards, which would need easement. If not, we would be able to place piping to help these people take care of their flooding issues. The runoff paths show that most of the water should be captured by these swales and taken to pond 3. With the 5 acres of land and the same regulations, previously described, there's 0.7 outflow for pre-development, so we must meet this using the detention pond. And with the detention pond of 0.2 acres on the plot of land which is available for purchase that would fit on this plot, we were able to effectively route it down to 0.5 CFS, which meets regulations. We also did the bankful for this pond, and it took 31 hours, which also meets the 24-hour regulation. It was then considered to route these two pond outlets to the Pine Lake outlet directly, since the elevation of the outlet at each pond was so low that it would be very difficult to connect it to the designed pipe network for the northern part of the neighborhood. There's also an alternate route where you could go straight down Hasler Road to the Pine Lake outlet if easements for backyards is not able to be obtained. You might also be able to create an open channel or connect it to the northern pipeline much further down in this network. For these pipes, they are 1 foot in diameter, but with such low flow coming out of both these ponds, they will not meet the 3 foot per second. However, with the detention ponds and the vegetation we recommended, this should filter out much of the sediment, alleviating the problem for sediment buildup and the purpose for the 3 feet per second. However, flushing of the pipes is recommended just in case every 10 or so years to make sure the pipes are handling effectively. And then for the northern part of the neighborhood, we did the same process of finding runoffs and creating sub-catchment areas with boundaries using high elevations and streets. We found out where the most optimal manhole placement is and where flooding problems exist. On this map, throughout blocks between Edson and Potter Street, there's flooding in backyards, and to the north there's more flooding in backyards, so we had to alleviate that. This is the simple pipe network which will handle the rest of the 35 acres of the Namoka village. It will be routed into a detention pond which is off-site. There's a forebay, there's ample space for a forebay for that in the detention pond. This detention pond will be 1.5 acres in surface area and will effectively handle all of this water. The green arrows represent swales, and these lead to the black arrows, which are pipes. For the 35 acres of land, the max outflow based on the regulations is 5.2 CFS, and the outflow from this pond using the pulse method is 4.9, which meets regulations. We then did the bankful again for this pond, and it took 36 hours, which again meets regulations. For a sustainable idea, we proposed that there could be swales on either side of each manhole, extending from the manhole to the boundary of the sub-catchment area, leaning in towards the manhole such that all the runoff will ensure be directed towards each manhole. The issues involved with this is acceptance from the public, as they might not enjoy swales throughout the whole neighborhood in front of all of their houses, and possibly safety issues with ditches in front of houses. This is a profile elevation of what I just described. These lines represent the sub-catchment areas, so all the runoff will come towards the swale, be collected, and drain directly towards each manhole.
So the last part of our hydrological design was to alleviate flooding in the Haslet Square parking lot, which is located at the southeastern part of our site. So what we proposed is to implement the use of rain gardens and rooftop gardens. They can exist where already there are parking lot buffers and sidewalk buffers and around the perimeters of the existing buildings. This will help reduce runoff and help with infiltration of the water. And our costs for hydrology, we considered excavation of different pipes and their diameters, swales and rain gardens, and we came to approximately $1.2 million for hydrology.
Use of poor drainage on site has resulted in poor roadway conditions. As the pavement specialist, I was asked to design a roadways or pavement structures to properly disperse water and alleviate frequent and ongoing flooding. I was also asked to prevent further distresses that were being caused by the flooding on site. These pavements were to be designed for a lifetime of 20 years. The first step in the pavement design process was to analyze existing pavement conditions on site. This can include an on-site visit, driving over the roads, gathering soil materials, information on the current pavement structures. The next step was to take traffic counts that were provided by our transportation specialists and project them to the design year to ensure that the pavements could handle the traffic loads that were expected in the next 20 years. The next step was to design the various pavement rehabilitation alternatives. Following this, an initial and life cycle cost analysis were performed for each pavement rehabilitation alternative to determine the most cost-effective strategy. The current pavement conditions on site, Marsh Road is a concrete overlay. This is concrete overlaid on asphalt. Hazlitt Road is asphalt. It was constructed in 2012. It's in fairly good condition. The neighborhood streets here are also asphalt with the exception of Colby Street, which is a gravel road. These are examples of the distresses seen on site. Top left here, you can see the rigid overlay on Marsh Road. That is where Lake Drive meets Marsh Road. You can see the asphalt to the rigid pavement. Up here, you can see alligator cracking as well as crack sealing. Down here, there's examples of potholes and patching that occurs. And here's an example of a drainage issue where water is pooling and causing pavement distress. To gather an initial evaluation of the pavement, I used the President Serviceability Index. This gives you the perception of the pavement quality based on ride quality. This wasn't used in design. I used it to gather initial conditions of the site. From this map, you can see 5 is the perfect conditions and 1 is very poor. Most of the roadways on site are fair to poor condition, with the exception of Marsh Road, which is the rigid overlay, and Hazlitt Road, which was constructed in 2012. The rehabilitation options considered for this project included complete asphalt and concrete reconstruction, an asphalt overlay with mill and fill, and a concrete overlay. These alternatives were designed according to federal, state, and local ordinances. The first step of our design process was to rule out alternatives that were not feasible. We felt that concrete in the neighborhoods wasn't feasible, it would be too expensive, and the roadways did not experience enough truck traffic to warrant concrete construction. The next step was to analyze the traffic, climate, and material properties of the site. This data was inputted into Astro design models, and this design model provided thicknesses for the pavement base and sub-base for each alternative, and Astro was used to design both rigid and flexible pavements. Following the design of each alternative, an initial cost estimation was formed, and using this, a life cycle cost analysis was performed on each method. There were 2 types performed. The first was a present worth analysis. This brings all future and initial costs to their present worth to analyze the most feasible option. The next was an equal uniform annual cost analysis. This analysis takes all the costs over the lifetime of the pavement and puts it into uniform annual costs, so you can determine the most economically effective one. And these analyses were used to determine the most cost-effective method for pavement rehabilitation. These were the chosen alternatives. For Hazlitt Road, we are recommending mill and fill to alleviate top-down cracking, which is already occurring just 2 years after construction. An asphalt overlay is being recommended for Edson, Potter, Shaw, and Lake Drive. Those are the roadways in the neighborhood. Colby Street, which was the gravel road, will receive an asphalt reconstruction. And for Marsh Road, I'm recommending concrete repairs, which include replacing roughly 15% of the concrete slabs, as well as sealing joints and other cracks on the roadway. This is the Colby Street Crossway, based on the ASHTO design. 2.5 inches of asphalt will be laid on top of the 2-inch aggregate base and 7-inch sub-base. This is a typical cross-section for the asphalt overlays in the neighborhood. The pavements range from 3 to 5 inches. The existing cross-section, the base is buried. Based on construction and other ordinances, 2-inch overlay is being recommended on top of the asphalt after following minor repairs to the current pavement surface. This is the Hazlet Road mill and fill. There's a 5-inch existing layer of asphalt. This will be milled down, remove the top 2.5 inches of the pavement, and then this will be replaced with new asphalt overlay to match the current cross-section and keep the current curb and gutter in place. Drainage solutions. Curb and gutter will be added to the rehabilitated roadways, be connected to the stormwater drainage system in some areas. That will be the black arrows, and the green arrows indicate where the curb and gutter will open up to swales. The roadways will cross slope to direct water towards the curb, leading to either the drain or the swale. And for Hazlet Road and Marsh Road, there is an existing drainage system which is adequate for the current conditions. This is a cross-section of the curb and gutter opening to the swale. This is the front view here. You can see there's openings along the curb and gutter. This is a top-down view. The water is allowed to go past the gutter into a filtration, which would be gravel or other aggregate, which will lead to the swale and continue onto the drain.
Okay, as the transportation specialist on the project, the main goal was to maintain traffic during all phases of construction and ensure that neighborhood residents and roadway users are being safe. So the initial stage for the design process was to estimate existing volumes for the link roads on site. From here, we were to design transportation infrastructure to accomplish drainage improvements put forth by the hydrologist. All available planning documents were reviewed, and local streets were to be designed for mixed use. A set of construction and removal plans was created, and we have them with us today. As stated, a maintaining traffic plan for staging and construction was to be completed. And finally, a detailed cost estimate for each project funding source was to be obtained. So, current average daily traffics were available on an online traffic database. And for roads where they were not available, assumptions were made on the basis of the ones that were. From here, we can predict our future traffic volumes for the design year, which is 20 years, by incorporating the growth rate, which for the pavement specialist on the project was determined to be 2%. And these current traffic volumes will prove useful when making decisions for our maintaining traffic plan. As stated, construction will be broken up to stages. Stage 1 will begin with pipe removal and installation. And during this stage, all of the local roads will be closed to through traffic, yet open to neighborhood traffic. It will be the primary focus of the engineers on site to ensure that during this phase, all residents will be made sure to be kept safe. And to get a time frame for removal and installation of pipes, we have our length of pipe to be installed within the neighborhood, and then we have our rate of installation, which was obtained from Michigan's roadway design manual. And using these two values, we can come up with our time of installation. For here, it was assumed that time for removal will be roughly similar to time of installation, which gives us our total time of approximately 70 days. Using, again, the Michigan roadway design manual, it was determined that catch basins with sewer inlets could be installed at a pace of about 4 units per day. And furthermore, any culverts needed at driveway approaches and sidewalks essentially can be constructed as fast as progress on sewer installation and removal allows. One thing to consider again for stage 1 is the storm sewer crossing underneath Marsh Road. With all this considered, we anticipate stage 1 to be completed in roughly 75 to 90 days. A few changes that came up in the project scope. The pavement specialist requested HMA coal milling and resurfacing of Hazlet Road, and also requested 15% concrete slab replacement of Marsh Road, which extended the scope of the project outside of the link roads in the neighborhood to the surrounding arterial roadways. So the maintaining traffic plan for construction stage 2, which will consist of pavement coal milling, resurfacing, and construction in the case of Colby Street, as needed for all roadways on site. Curb and gutter is to be placed before paving begins at a rate of approximately 1,200 feet per day. And given that we have about 11,500 linear feet of curb and gutter to be placed, we assume it will take about 10 days to place all curb and gutter. MDOT maintaining traffic typicals were utilized for the arterial roadways as a road and Marsh Road. And due to low volumes that were determined earlier for Edson, Potter, Shaw, and Colby Streets, it was determined that it would be possible to shut these down completely during paving operations. And details pertaining to this decision will be discussed further. All this considered, we anticipate stage 1 to be completed in roughly 20 to 25 days. Okay, so just justifying our selection for the lane width of Colby Street, which is to be constructed with HMA. We decided to incorporate 10-foot lanes with curb and gutter, and that's on the basis of current average daily traffic volume and the type of road that Colby Street is. Tying back into our decision to close roads down during paving for local streets, using total length, asphalt needed, and our rate of paving, which was obtained from the Michigan Roadway Design Manual. You see that days needed for paving for link roads is significantly below 1 day. In the case of Hazlet Road, we see that using our rate of HMA coal milling, that it would be approximately 1 day for milling, and down here approximately half a day for paving. That being said, construction operations for Hazlet Road will be done 1 lane at a time. So a day buffer was added to this total of approximately 2 days to bring it to 3 days. And finally, for Colby Street, we anticipate construction to take approximately 4 days. Just reiterating the amount of time for paving operations to take place for each road. Here we have some pictures that were extracted from MDOT's maintaining traffic typicals. This pertains to the crossing of pipe installation underneath Marsh Road. In the interest of keeping traffic open and flowing, we elected to break this into 2 phases and essentially make this portion of Marsh Road a 2-lane, 2-way road as opposed to a 4-lane, 2-way road during this construction process. Pertaining to stage 2, the coal milling of Hazlet and the slab replacement of Marsh, we will, again, in the interest of keeping traffic open and flowing, perform construction 1 lane at a time. In the case of middle lanes, 2 lanes at a time. It should be noted that MDOT has rules and regulations to sign placement on site on the basis of the roadway type and roadway speed. During Marsh Road construction, some alternate routes that roadway users could be encouraged to take to distribute traffic would be to head west on Hazlet Road north on Pavement Avenue, and finally back east on Lake Drive. And here we have alternate route 2, assuming that Edson has complete, well, actually this will be prior to phase 2, so Edson will be in its current condition. However, we will reroute traffic east on Hazard Road, north on Edson, and finally back west on Lake Lansing. Because the pavement specialist elected to go with HMA overlays of all linked roads, geometries were to be unchanged. With this considered, it was deemed cost ineffective and not feasible to implement bike lanes into existing link roads. Therefore, we elected to go with sidewalks. All sidewalks will be at least 5 feet across and will be in accordance with current Americans with Disability Act standards. Here we see a typical ramp with a 2-foot long approach, so blind roadway users can detect the ramp. Here we see a typical swale cross section. A recoverable slope was implemented, typically 1-on-3. Culverts were to be constructed at driveway approaches where swales were present, approximately 12-inch diameter culverts. A total of 22 culverts have been placed on site, as well as 33 sewer units, which can all be seen in the plans we have listed. Considerations for pavement marking and signing. Due to the low volumes of the link roads, it was deemed unnecessary and cost ineffective to paint any lines on Edson Street, Potter, Shaw, or Colby Street. With respect to construction operations on Hazlet and Marsh, the contractor shall log current pavement markings to be remarked after HMA resurfacing and slab replacement for Hazlet and Marsh respectively. Currently, stop signs do exist on either side of Potter Street, Shaw Street, and Edson Street, and crossing Lake Drive. And 4-way stops occur at every intersection of Colby Street. So all these signs are to be noted and remain intact or be replaced upon completion of construction. Extending the scope outside of the Mocha Village as a transportation specialist, I was to design a non-motorized pathway, extending the interurban pathway from its current terminal point to Hazlet Road. Decisions made throughout this design process were made on the basis of favorable topography, available space, and geometry. So here we see the existing interurban pathway. It forks off and has a terminal point here. And on the basis of the criteria described in the previous slide, we elected to design the pathway to extend within the right-of-way of Consumers Energy along the railroad, underneath the Marsh Road, and finally connecting to Hazlet Road. Here we see a cross-section of the pathway. It's to be 14 feet across with approximately 2% cross grade for drainage purposes. It will have 4 inches of asphalt to be laid in 2 2-inch courses, and finally a 6-inch aggregate base. Here we see a typical station cross section. The idea here when creating these was to have the amount of earth needing to be excavated cancel out the amount of earth needing to be placed, and this is called balanced cut and fill to minimize earthwork costs. And here we see how the bicycle path sits on a nice horizontal plane. The x-axis corresponds to the right-of-way of Consumers Energy, which is approximately 40 feet. And then the y-axis corresponds to elevation. So you get an idea of how the bike path will leave within the right-of-way that we're leaving. Some considerations for the upcoming bridge construction on Marsh Road. This station corresponds to the location that will be underneath the bridge. Currently it's oriented about 8 feet off of the north side of the right-of-way of Consumers Energy. So if any new piers are to be constructed during construction of the bridge, it's important that our current orientation at this station for the bike path is noted. Finally, see the bike trail profile, both existing and proposed. The main concern here was keeping the profile cap below 5% grade, which corresponds with the design speed of the bicycle path, which is 18 miles per hour, to ensure that all users can maintain control of their bicycles. And again, reiterating that idea of a balanced cut and fill to where what's being in cancels out what's being taken out cancels out what needs to be placed. So the total cost for the project that we're proposing: hydrology, as stated, roughly 1.2 million. Transportation, which corresponds with sidewalks being moved and placed, and the inter-urban pathway just described, approximately 270,000. Pavements, 620,000, to come to a subtotal of approximately 2.1 million. And some other costs to be considered are that of inspection and testing, approximately 100,000. Our engineering fee, approximately 300,000, and finally a contingency fee, which essentially just serves as a buffer of our estimate. All coming to a project total of approximately $2.7 million. And now we'll open it up for any questions or comments.
Thank you. Start on this end of the side. I'm Tyler Dawson, MTH Consultants, and I'll ask some questions here, mostly on the pavement. We'll start with your outlet for retention pond goes under Marsh Road. Did you consider horizontal directional drilling or a trenchless method to install that instead of having to close Marsh Road?
Yes, we did. Speaking with the pavement specialist, or the hydrology specialist, we felt that the drilling would be feasible. It would be easier just to remove the pavement on Marsh Road and just lay the pipe underneath it.
Is the county or the road owner okay with that?
We haven't spoken to them now.
Okay. So you had a slide on the PSI rating of the roads. I was confused about what you used that for.
That was just, the PSI was just used, sorry, let me find that. The PSI was just used for me to gather an initial evaluation of the pavement. It was kind of just to let you guys know the conditions based on how a driver would perceive the roadway conditions of the roads on site.
Okay. So how did you decide what, as far as your treatment, your overlay, how was that determined for the neighborhood roads?
How was the thickness determined, or how was the
How did you determine that's what you needed?
an overlay? That was based on ASHTO design. Determined an overlay was needed because of the stresses on site, just going out there and evaluating. Also based on thicknesses and age of the pavement.
You think that the overlay is going to last for 20 years?
I think it will if the road is treated before the overlay is placed down. I've designed it and I've also checked it in program MEPG to ensure that the overlay will last with the current pavement conditions.
So you said, so you're going to do some pre-treatment to the existing pavement?
Correct. Any patching and any areas of severe distress, we would encourage a localized mill and fill.
Okay. Your new design for Kobe Road, the one that's currently not paved, I think you had a 2.5-inch HMA. Is that consistent with the county's minimums?
The county recommends a 5-inch HMA layer. We felt that that was a over-design. Based on ASHTO, we got 2.5 inches to last the pavement 20 years. This Colby Street essentially serves a limited amount of lots. We felt that due to the traffic that the regulation was an over-design of the pavement.
Okay. For Hazlet Road, recommending a mill and fill surface. How deep mill and fill would you say?
2.5 inches.
How deep the top down cracks are?
That was just an estimation just to ensure that the cracks would be removed that I observed on site. I don't have the pavement course to tell you how deep the top down cracks go, but just estimating on observations, that's what I assume.
It's only a couple-year-old road, so we hope they're not that deep. I want to take some tours and see if they're going to less and reduce the amount of work in dollars there. Didn't say anything about the hot mix asphalt for your overlay or mill and fill. What PG grade you're using?
The PG grade is a 58-28. This is determined by the LTTP buying program. Just 58 is the average 7-day pavement temperature, and negative 28 degrees Celsius is the low temperature for the pavement. And that's what the HMA was designed for.
Okay, you have a mix gradation selected. You showed 13
I have it.
for the.
I have it. I don't have it on these slides.
Okay.
I'd have to look at my notes and let you know what the gradation is.
As far as Marsh Road, you showed alternatives for detours, but you also showed traffic control chemicals. Are you closing Marsh Road, or are you giving 3 options of detour?
It'd be a 2-lane, 2-way, and as users would be approaching the intersection, they'd be made aware of construction and encouraged to use alternative routes, but Marsh would still be.
Okay, so just an option, 1, 2, or 3. This is my last question on the bike path, talking about having equivalent cut and fill volumes. What kind of material are you cutting? Is it going to be acceptable for use as a fill material?
That wasn't analyzed on the basis that we already had designed the 6-inch aggregate base. Whether or not that sub-base would be sufficient was not.
You're going to reuse the material. Most of the site material, I believe, is cohesive. Probably not suitable for backfill, so thing to think about more.
Okay, I'm Dave Love. I work with the Grand Commissioner's Office, so I'm pretty familiar with this area. I'm intrigued by your idea of the bike path, and I think that's probably a good idea. One of the things that happens is sometimes you wind up cutting off existing drainage patterns, and I didn't see that you've taken into consideration drainage under through the trail at all. Is there any consideration for that, like swales on each side, or?
There hasn't been, and I think that's due to the fact that that portion of the project was just something that I was doing on my own. The hydrologists weren't really working with me, and so really all I was considering throughout that process was safe profile slopes. But that's something that definitely could be looked into.
I think that's bad. On the hydrology side, I'm curious as to where you got your rainfall map from.
We took it from MDOT.
Because I guess I haven't seen that map before. It winds up giving us more rain than I thought we had here, so I'm curious as to if that's on the website.
It was taken from the last MDOT rainfall reports on their website.
In thinking about swales, you made a comment about the possibly they wouldn't be accepted very well. And wonder if you could expand on that a little bit.
Well, the residents have the option of having it or not because they're able to fill it in if they really wanted to, since that would be part of their land. And I'm not sure everyone would enjoy a 6-foot wide ditch in front of their house.
Something to be considered with that 66 feet given for the road right away. All the swales fall well within that 66 feet.
So they're all public, and they would all be in public right away.
Yes.
Are sidewalks being proposed for all streets?
Yes. With the exception of some sidewalk that exists on the east side of Shaw that was determined to be in good condition.
As far as the swales as well, some of the houses were very close to the road, so these swales would be very close to their property. And that's one of the other considerations we took with the swales in our design.
And with sidewalk, there was a few areas where sidewalk couldn't be implemented because it was getting dangerously close to that right away. So as long as they don't fall within the property lines of homeowners, that's where sidewalks will be.
Okay.
Could I just jump in on that for a second? If the swales that residents might not like it, maybe there's not room in the house, why not just capture and enclose everything?
Well, we wanted to have some, consider like sustainable and green design. We saw that as having these swales, maybe with some greenery. You could kind of spice up, maybe put a bit.
Project could also be designed in the same locations, serve the same function. We just figured more sustainable, the better.
Well, just as a quick aside, we just, as the drain office, just built a similar thing just like this in Colton last year. And just to let you know, the sidewalk portion was a lot trickier than the swale portion. Because of dodging on trees and power poles. And it probably haven't thought about how much cost there really is involved in that.
Admittedly, as far as going house by house to see which obstructions would come up, that wasn't done for the scope of the project. But that's understandable that maybe we're assuming something would be a lot easier said than done. That being said, the scope was to design for mixed use, so that's why we didn't want to incorporate some kind of pedestrian transportation.
Very good. Okay, I have one other question, and that's about the commercial area. You talked about doing rain gardens and green roofs, I guess. So you calculate that out to show that you're going to be able to hold all the water from that?
Yep. I found the drainage area to be approximately 290,000 square feet. And there was a Southern Lake Michigan rain garden manual that I based off my calculations, and I needed about 11,000 square feet of rain gardens. And I did meet that. I had 11,200 square feet.
And do you have soils information to tell you where the water's going to actually go?
No. But I do have, we're probably going to have to bring in some new soil because the current conditions aren't, will not infiltrate very well. We would have about a 50% layer of sand, and compost, and topsoil for the other 50%.
Okay, very good.
That's all my question.
Greg Matthew with LSG Engineers and Surveyors. I'd like to pick up on where you're at in that discussion with the rain gardens, and you're going to put some sort of infiltration layer in there. And then my question is then, good, where's it gonna go once it gets past your engineering field?
I began to design for an overdrain pipe network within the parking lot, but I ran out of time. So this is what I had 100% and why we have enough space. It can be implemented for an overdrain. Yes, sorry.
Your rooftop gardens, how much water are you storing on top of those roofs? And at what depth?
I don't have exact area calculations, but I think they should be slanted so that they would capture. I'm not sure.
What I'm getting at is, what kind of water volumes have you got on top of these roofs? How much water are you putting up
I have the area of the rain gardens, but
there? What I think you need to know as a starting point is what volume you're putting on top of this, what kind of depths you're looking at. You've got a weight associated with the water, correct? So, there's a couple of things I'm thinking of. One is, what kind of a structure you can have up there? How are you gonna hold that water? What's the bathtub gonna look like? And what kind of weights are you looking at? Consider all the roofs that collapse because of snow loads. Now this roof may already have been designed. The roof obviously had to meet building code. It probably does, I'm sure. Are you imposing more load than that snow load might have? Are you going to have issues with your structure?
it wouldn't impose it would not, if it's designed for snow properly, which I'm assuming it would be able to handle all the weight.
Do you know that the load you're imposing with that water, do you know that it is equal or less than any snow load that will be imposed?
I don't have the numbers, but I know from my experience that the snow loads would be much heavier.
I would expect that would have been investigated.
This was actually, it was more so an additional side thought for extra filtration because my design was incomplete. So I don't have all the actual data, but it should work.
We might need to consider a piping network through the parking lot. However, we didn't know if it would be feasible that they would completely repave the parking lot and pay for the entire drain to be placed between the middle of the parking spaces and down or up towards the rest of the village.
Can we look at the graphic that shows your layout for the southern of the detention ponds in the Mocha Village plat area where you show your line running out to the outlet drain? Yes, yep, right there. I've got some real issues with your willingness to violate some basic design criteria, such as your low velocities in the pipe. Knowing that you've got some downstream issues in piling outlet drain. Have you considered, as you're looking at this layout and thinking about in terms of water surface profiles, for example, did you look at flood elevations in the Pine Lake outlet drain?
Yes.
And what are the flood elevations that are relative to some of what you're looking at through water surface?
The flood elevation, they're at 848 feet, so it reaches out like to here and extends up this way.
What's your invert elevation? Do you know an invert elevation for your outlet pipe?
The outlet pipe for this detention pond's at 845 and 847 for that one.
So you're below you're designing your extension area for 100 feet, correct?
Yes.
So when you're considering your 100-year elevation at your outlet point, you've got an invert that's below that 100 year. very low flow rate coming out. Is it possible that you may have water from primary outlet drain backing up through your outlet system and therefore not be able to actually do outflow? Without sufficient force to push its way out?
Based on the ponds being full and then outflowing, there should be some force backwards. I don't know if the water would have enough force from the under-gear flood to rush all the way back up the pipes.
You think it's worth considering?
Yes.
I have a question about productivity rates for construction. Where did you come up with those? What was your basis for that? You have X amount of days for pipe installation, X amount of days for paving, etc.
I've got roadway design that gave a rate like from installation of like the size of the pipe that we're using and the type of environment that it's being installed into, and just took the linear feet that was being installed within the neighborhood, divided into the estimate for installation.
Let's stay on this spreadsheet for this moment. You're looking at installing pipe, and you're also looking at removing the pipe. Do you have instances where the pipe that you're removing is in roughly the same location as the pipe you're installing, or is all pipe that's being installed in an entirely different location than the pipe that's being removed?
Most of the pipe that we're removing is following generally the same path which we designed.
So as you're excavating the trench to install the pipe, you have to be in the same vicinity where you need to be excavating to remove the pipe?
Yeah.
So,
So this time here is.
so what's the potential impact there in terms of your time estimate? Would you revise your time estimate
I would
based on that?
Yeah, with further discussion with hydrologists, and to be honest, we didn't get to that point. This number here would probably be lower.
However, we would have to remove the pipes for where we designed the first 2 detention ponds first so that we could build the detention ponds. So this time could be closer to accurate since I don't think we'd be able to remove and place at the same time.
Could I see your image for your alternate route number 2, please? Sure. You mentioned earlier in some of the discussion, the earlier question about designating these alternate routes. Who are you proposing is going to be taking these alternate routes?
Well, definitely not truck traffic. As far as optimizing signal times to accommodate for this route, that was not done. But
You had an image, and I know the basis of it was the National Design Guide, which you needed to have shown in your graphic, but for that Ensign Street there, I believe you were advocating you were going to be able to use smaller design widths on the pavement because you had low AETs, correct?
well, all the geometries of these 3 roads were not going to be altered because of them receiving overlays.
Geometrically speaking, and also in terms of pavement thicknesses, at whatever time you think you're going to be using Ensign Street as an alternate route, is it sufficient for the traffic that you're going to be putting through there? Because you're basically talking about taking Marsh Road traffic and putting it through there. Even if you say no trucks allowed, just looking at passenger vehicles, is it going to be able to hold up to that?
It would be only for
Safety consideration.
for during construction, and this is, I believe, prior to the asphalt overlay.
Yeah.
So any distresses that would occur from that traffic could be addressed before the overlay. As well as this won't be entire Marsh Road traffic. They will be able to use alternate Route 1 2 as well as Marsh Road will be open as well.
One thing you want to consider in this is driver's ability to react. And now what you're telling me is you've got basically 3 alternatives at some point in time. There's a point where you're constructing Marsh, you're going to have, or conducting your work on Marsh, and you show maintaining traffic detail, suggesting that you can still get traffic on Marsh, but now you can also go this way and also go that way. How much confusion do you want to generate at that intersection of Marsh and Hazlitt or Marsh and Lake while drivers decide what's going to be my best route? What do I want to do here?
I wasn't proposing to make like force traffic into these routes. The maintained traffic plan would be implemented for Marsh. And with that traffic plan, if there was still going to be some congestion, all these were was just showing that drivers could take this route if congestion does occur with Marsh's
I want to make my question/comment a little more forceful. It's you got to make a decision for the driver at this point during your design. You have to decide.